Hey subscribers, welcome back. This is going to be a brilliant introduction into prime factors and prime factor decomposition. Now there's a few definitions we need to learn first, and then within the next few videos we'll be looking at more formal methods for prime factor decomposition, but you're going to need to know what prime factors are, you're going to need to know what factors are, what prime numbers are, and a few examples of just playing around with these ideas. So we'll get started with some definitions and then we'll do some examples. So the first thing you need to do is just check you know the definition of a factor. So a factor is a natural number that divides exactly into another number without a remainder. So a natural number is a type of number that you may start counting with as a child, like 1, 2, 3, 4. We're not talking about decimals, we're not talking about fractions, and we don't typically include 0. In this case, we're not going to include 0. So it's just positive whole numbers. So anything that goes into another number without a remainder is considered a factor. Now, this is just a visual representation of factors and non-factors. So for example, in the case of 6, well, we can see that 3 goes into 6 twice and there's nothing left over. We can see that 2 goes into 6 3 times with nothing left over, and we can see that 1 goes into 6 6 times. So the factors of 6 are 1, 2 and 3, and there's one that people always forget, which is 6 also goes into itself once. So don't forget the 6. The two most common things people forget are the 1 and the 6 itself. So we can see that 6 has 4 factors, 1, 2, 3 and 6. And for the number 5, you can see here, well, 5 goes into 5, 1 goes into 5 times, so 1 and 5. Now the 2 is an example of something that doesn't go in, because you can see that, well, if you put 2 2's you get 4, but then there's an extra 1 unit remaining, so 2 does not go into 5. So this is the big idea behind factors. Now another definition is that we need to know is what a prime number is. So a prime number has exactly 2 factors. It can't have more, it can't have less. So exactly 2, that's why it's underlined. And we'll look at some examples in a minute. A composite number sounds a bit like the opposite of a prime number, but is not exactly the opposite. It's just a number that has more than 2 factors. So anything with more than 2 factors is considered to be a composite number. All prime numbers cannot be composite numbers, and composite numbers cannot be prime numbers. Now, the reason they're not exactly opposites is because there's an odd case, and that's the 1. 1 is not prime or composite. It's just a special case. Historically, some people have considered 1 to be prime, but in the modern day, we don't consider 1 to be a prime number. And for our content, we're not going to assume it is either. So some examples of prime numbers, if I go back to this example here, we can see that 6 is a composite number because it's got more than 2 factors. So in fact, it's got 1, 2, 3, 4 different factors, 1, 2, 3 and 6. And then 5 has exactly 2 factors, which is 1 and 5, not the 2 obviously. So in this case we can see that this is a prime number. And then 6 is a composite number. Okay, now some examples of the prime numbers up to 100 are listed here. The first prime number is 2, and it goes all the way up. And we got to 97 here, but actually these dots are important because the prime numbers go on forever. Generally speaking though, we're going to use the first few prime numbers, 2, 3, 5, 7, 11 and 13. You should know those very quickly off the top of your head, so make a note of those if you don't already know that. Common mistake is people include 1. 1 is not a prime number, just remember that. So remember, a prime number has exactly 2 factors. 1, in the case of 1, the only factor is 1, so it's only got 1 factor. Okay, so let's do an example of using things like factors and factor pairs. So pause the video and have a go with these questions, and then I'll go through them with you. Okay, I'm going to go through these with you now. Now Rosie is listing the factor pairs of 18. Is she correct? Well, factor pairs are pairs of numbers that multiply to give you 18. So 1 times 18 is correct. 2 times 9 is correct. That will give you 18. 3 times 6 is also correct. 4.5 times 4 is correct in terms of it giving you 18, but it's not correct in terms of a factor pair. It is a pair, but you can't call 4.5 a factor. 4.5 is not a natural number. It's a decimal, so we don't count this. So she's correct for the first three, but not for the last one. Now, if we write down all the factor pairs of 24, we can also make a list here. So this is asking for factors, not factor pairs. If you wrote factor pairs, that should be fine, but this is just an example. I'm going to do it now. So 1 times 24, 2 times 12, 3 times 8, 4 times 6. I'll just move this to the left, to the right. Another 5 doesn't go. And if we go to 6 times 4, you can see we're actually repeating here. So we're going to stop here. Now, all the factors of 24 are going to be 1, 2, 3, 4. So it's these 4 numbers here, and also those 4 numbers. So that's going to be 6, 8, 12, and 24. Okay, now in the last question, we're not going to go through this in detail, but hopefully you've come up with numbers, for example, 30, 60, 90, and that goes on. Okay, so we've looked at factors, factor pairs, and making lists. Let's go into a bit more depth now. Now, if I want to arrange something into rows and columns, I put them into something called an array. And an array is, for example, if I had 6 cupcakes, I could do this type of array. 1, 2, 3, 4, 5, 6. So this is a 2 by 3 because it's got two rows and 3 columns. Now, if I had 12 cupcakes, how many different arrays can you make? Pause the video and just use crosses for this example. You don't need to draw cupcakes, but how many ways can I arrange 12 into an array? I'm going to show you the first example. That's going to be 2 by 6. How many more can you come up with? Pause the video, have a go. Okay, I'm going to show the answers in 3, 2, 1. Okay, so another array could be a 3 by 4 array, and another one could be 1 by 12. Now you might rotate these arrays, and you might do 6 by 2, or a 4 by 3, or a 1 by 12. They're all correct, but we're only going to count the first arrangement. We're not going to double count these arrays. So these are, because of the commutative law, we're going to count them as the same thing. So 2 by 6 is the same as 6 by 2. Now, what you've actually done here is these arrays show factors. So 2 is a factor of 12, 6 is a factor of 12, so is 3 and 4 and 1 and 12. So how about the number 5? Now you can see the array doesn't quite work because we've got a remainder of 2. Now I've shown it 2 different ways. It's up to you where you put the final 2 cupcakes, but you can see it doesn't quite work here because of the remainder. So we can say that 5 is not a factor of 12.